welcome to the forces review. So this is going to be focusing on Newton's laws of motion, no rotation. That will be a separate video that is going to ideally be coming out soon. So previous content, again, where you can look for some Newton's laws of motion. So we covered this lectures 7 through 10, homeworks 4 through 8, worksheets 4 and 5, quiz 4 and 5, and then a little bit on exam 1 and 2. So a force, again, is defined as any push or pull. This can be physical contact or this can be a long-range force. The long-range forces we've been dealing with in this class being gravity as well as Coulomb's law, so the force between charged interactions. So we are going to be focusing on non-Coulomb's law stuff. For two reasons. One, nobody asked for a review on that, and two, this content is a lot older, so it makes sense to recap on some of the older stuff more so than the new stuff. It is a vector with SI units of the Newton, which is a kilogram times, it should be meters per second squared. But anyway, this vector behavior means that we need to figure out which direction the force is going to point into. Now, when we first introduced forces, these are the ones that we looked at. We are not going to be dealing with drag. Let's just, oops, it's not black. We're not going to deal with drag. We're not going to be dealing with thrust, so we can just completely ignore these and not have to worry about them when it comes to the exam. However, we are going to need to know about gravity, maybe spring, probably not. Tension, normal force, static, and kinetic friction. So again, with the notation that is given here, this is the notation that the textbook uses. You do not have to use this particular notation. However, once you use a notation for a question, you need to continue using it for the remainder of that question. That way I can compare your setup to your next part of the question. So the textbook in chapter 5, section 2 goes into more information about some of these. In particular, over the next couple of slides, I am going to be going over tension as well as the two frictional forces in this class. But if you need to look at gravity, again, the equation we were dealing with is mg, spring force if we have it negative, k, x. Normal force you're going to have to solve, but it's always going to be perpendicular to the surface. And then the remaining forces let's talk about in a little bit more detail, starting with friction. So everything about friction is in chapter 6, section 4. So we have primarily two types of friction we're going to be looking at in this class. Right? We did talk about rolling friction and then proceeded to never use it again. So the only frictions we are going to be dealing with are static friction and kinetic friction. The equation for static friction is technically the force of static friction, and it is the maximum value, which is going to be the coefficient of static friction times the normal force. Now, in reality, you can have multiple values for your static friction force. It is not something that is going to be constant. We have this situation where in a lot of questions we're looking at the maximum force it takes to pull something, the maximum frictional force some way, shape, or form. So we're almost always exclusively dealing with this situation where the frictional force is equal to mu Sn. That is how we have been dealing with it in this class, and that is going to be how we continue to deal with it. But it is important to note, and it's been on I think it was first on a quiz and then it was on exam, I want to say it was on exam 1, it might have been exam 2. There's the question with the two boxes being pulled. The boxes have a different mass, but because the force pulling is the same and they're both not moving, the static frictional force value is counteracting that force. It's the same. but the maximum value for friction would be different. So again, we are primarily going to be using this condition where the object is just about to slip. So some key words to look for static friction is if the object is at rest, it's stationary, or you're looking for something associated with maximum friction. The other type of friction that we've been dealing with is kinetic friction. So it has a different coefficient of friction, so mu sub k times the normal force. So that means that the symbol or the variable used for kinetic friction is lowercase f with a k for kinetic. Now the kinetic friction is a constant value once you are sliding around on a surface. This is the value you are going to have for your kinetic friction. Some key things to look for is objects sliding on another object. So if usually what we have been having, so you have one stationary object and something like a box sliding on that object. And we will be doing an example that has kinetic friction in it shortly. The other thing we need to talk about is tension. So we are dealing with nice, ideal strings and ropes. And that means that they are going to be massless and the tension is going to be constant throughout the rope. However, if you go and look through section 7.4, it talks about how the rope really has a bunch of different little components on it, and they are pulling in opposite directions. But we're not really always going to be, we're never going to focus on that interpretation of the rope. So what we need to focus on is tension is going to follow Newton's third law. It is constant throughout the entirety of the rope, so it's going to pull on both objects with equal magnitude. So the way that the textbook goes through to describe how we can ignore the string as an object is there is tension from the string on box A, and that is equal and opposite, according to Newton's third law, of the tension from box A onto the string, and the same is happening with B. So these are equal and opposite, so usually we just say, well, tension pulling A to the right is the same as tension pulling B to the left. So typically, we just call this tension, and then we ignore everything exactly happening in the string. Equal in magnitude, opposite in directions, it is pulling both boxes. Tension never can push an object. It is always going to be pulling. Now in the situation of where we have a pulley, the magnitude of tension is not changed. Only the direction is going to be changed. And so what that means is that, again, we are going to be able to use tension in both objects, because if you have tension, you have to have either an external force or an external object creating that tension, or you have two objects with the same tension. You may need to use that tension to connect the two mathematical representations together, just like how it connects them physically to each other. So if you have a single string, tension is constant, better be the same exact value on both objects, and with that, it is going to, pull both of them. So it's always going to point in the direction of the string. So on box A here, tension is going to point to the right, towards the middle of the string. And for box B, it's going to point to the left, again towards the center of the string. So let's actually talk about Newton's laws of motion. Newton's first law of motion says that the net force acting on the object is 0. and that means that the mass times acceleration is going to be 0. In Newton's first law, an object is either at rest or moving in a constant or at a constant velocity in a straight line. Those are the two situations in which we have Newton's first law. More often than not, when we've been using it, it's just we are not moving in that direction. We are stationary in the y direction when we tilt our coordinate system correctly. Newton's second law is that the acceleration is equal to the net force divided by the mass. This is the formal way in which it is written out. However, typically when we've been using it, we have mass times acceleration is equal to the net force. Same equation, is just how you typically write it out is the one on the right, even though we're technically 95% of the time solving for acceleration. Newton's third law says that forces come in what are referred to as action-reaction pairs. Technically, we don't know which one is which, but what it says is that these action-reaction pairs are equal in magnitude, but opposite in direction. So here we have force A on object B is going to be equal to the negative force from B onto A. Equal in value, opposite in direction with that negative sign. Now, again, force is a vector. Because force is a vector, we are able to treat the x and the y directions separately, and this is something that you have to do in order to go through and solve these questions. The reason we solve Newton's laws the way we do is it allows us to make sure that we're keeping x with x, y with y. So it's going to be important to choose coordinate systems and then stick with them once we go through and solve the question. So let's talk about free body diagrams and using Newton's laws. So a free body diagram is that thing I tend to make you draw at the beginning of a force question, where you have to draw all the forces in the roughly correct direction with the roughly correct length. So when solving Newton's laws problems, the first thing you should be doing is identifying all the forces acting on the object, and you should draw and label these forces on the object. So step 1 is to do the free body diagram. The second thing you should be doing is choosing a coordinate system. Each object can have its own coordinates. And again, you do not have to stick with the standard coordinate system. If you want to tilt it, you are welcome to tilt it. If you want to keep it to be the traditional x to the right, y to the positive up direction, you're welcome to do that. It's your choice, but once you've chosen your coordinate system, you must stick with your coordinate system throughout the rest of the question. So choose smart coordinate systems. Make your life as easy as possible. Step 3 is going to be determining if you have the first or second law in each direction. Again, this is based on the coordinate system you literally just chose. The fourth step is setting up each direction, so the x and the y direction. Again, if you feel spicy and you want to use z, go for it. Just make sure that you show which direction z is. Again, you need to use your coordinate system to set this up. You're then going to go through and solve for any knowns, or sorry, not solving for knowns, you're solving for unknowns. You may need to combine different directions together. So for example, if you have friction, you might need to use the y direction in order to solve for the normal force to solve for a frictional force. You might need to use the tension for the two objects connected to each other to help you find the acceleration between the objects. You can't isolate one object 100% by itself in order to go through and solve if there are two objects in your question. All right, so here is an example that we are going to be working through. So what I would like you to do is pause the video, go through and actually try to solve this question. And before you get confused, yes, this loops around. I'm just not very good at drawing the looping part in Excel. And for the sake of it's already on the ground arguments, there's more stuff down here. Just didn't draw the space for it. So again, pause the video, go through and try to solve this question as if you were trying to do it for an exam. So I don't really have a lot of space on here, but I'm going to be doing my best to try to draw both of these. You can see that I am including a very key sentence here that hopefully you will remember to do, is you must must include coordinate systems for both boxes for full credit. That means you need to draw both objects to have their own coordinate system. So I'm going to shove these on here just so we can make sure we're looking at the image correctly. So for A, it is on an incline, which means that the normal force is going to be perpendicular to its surface. The force due to gravity, I need to indicate that this is for A, or I could write MAG. That needs to be there. And I have the rope pulling on box A. So with this, we aren't told anything about friction. Right? There's no information that, oh, wait, there is. It explicitly tells us to ignore friction. So that means we don't have to deal with friction in this question. Makes our life much simpler. We don't have to include that force. So for box B, it's going to have tension pulling upwards, and it's going to have gravity pulling it down. Again, I need to indicate that this gravity is the gravity for box B. Now I need to think about a couple of things. I need to draw my coordinate systems. Now my personal preference is to like it as I don't want to have a negative acceleration. So I want to figure out which way my objects are moving. It tells me box A is allowed to move down the incline, pulling box B upwards. So this question does tell me the direction in which my boxes are moving. So because of that, we need to go through and do this. I just saw the note that I made for myself when solving this. I need to move my decimal place over, and I didn't do it here. Did it on one version of the PDF, but not another. It should be 1.22 kilograms for the mass of B. So just my bad. So mass B is going to be 1.22 kilograms, not 12.2 kilograms. If you do 12.2, B actually moves down and A moves up the incline. With 1.22 kilograms, they move the correct direction. Anyway, so I'm going to put my Y direction for box A in the direction of the normal force, and I'm going to put X pointing down the incline. Because I want box B and box A to move in the same direction, I'm going to say that up is positive X, and to the left is Y. I don't have any forces in that direction, so I'm not going to have to worry about it. So that's going to make my life simpler. So I now have part A done. I have all the forces I need to deal with. I have the tension from the rope that is connecting both boxes. Because this tension is constant, I'm using the same T to describe tension. I only have one normal force that's going to be on box A because it's on the incline. B is not resting on a surface. There is no normal force to be had. Both have gravity. So I've indicated that I have gravity of B and gravity of A because they have different masses. So for box B, we are actually being asked to solve for the acceleration. And then in C, we're going to be finding out the velocity of box B right before it collides with the pulley. So right before B strikes this pulley, what is its velocity? We do have the distance it's traveling. We're solving for the acceleration. It's starting from rest. It tells us that in the second sentence, the boxes are let go from rest. Have the starting value, just need the final one to go through and solve. All right, so let's go ahead and start setting up our laws of motion. So let's look at box A first. I'm going to have the normal force minus mg cosine theta, and that's going to be equal to 0. Again, the reason that it is cosine, so if I draw gravity, I'm just going to use capital G right here. I have tilted my coordinate system so that positive y is over here. Positive x is now here. The old direction for negative y is in the same direction as g, where the new direction of negative y is opposite positive y. That's how that works out. So I've shifted some theta value. That theta value being equal to the change of my axis. I've gone from g to y, or sorry, g to negative y. My y direction is then going to be tangent, or sorry, adjacent to my angle. It is going to be cosine. If I look at AX, again, going back to my free body diagram, I'm going to have only, oh, sorry, there should be an A here, MAG sine theta. Again, some amount now is pointing in my X direction. It's going to point in the positive X direction, so my force should be positive, minus tension is going to be equal to MA times A. So I actually do not need my Y direction in this case because there is no friction. If there was no friction, I would need my Y direction for box A in order to go through and solve. Now I want to do the same thing for box B. In the Y direction, I just have 0, so that makes it nice and easy. For the X direction, I'm going to have positive tension minus MBG. And this is going to be equal to MBA. So before we go through and try to solve this, I want to talk about why my answers are the way they are. So for A, tension is pulling up the incline, which we have established is the negative X direction. So this needs to be negative. By saying that up is positive X for box B, my acceleration is now going to be in the same direction. This A here and this A here, both of my accelerations are going to be the same value with the same sign because I've put my positive X direction in the direction of motion. If I said down is positive for my X direction, I would need to include a negative sign on one of my accelerations. So by putting both coordinate systems such that the same direction is the way you are moving, so in this case positive X, I can look at my X directions together and my acceleration is going to be the same magnitude and both going to be positive or both going to be negative. So this is a really important tool to use in order to make, you don't have to do anything at the end. When you've solved, you solved and you are good. So I really have two equations I need to deal with because 0 doesn't really mean anything. So if I look at my equation for the x direction for A, I have two unknowns. I don't know my tension and I don't know my acceleration. If I look at my forces for x for B, I don't know tension and I don't know acceleration. It's the same values, so that means that if I solve one equation for tension, I can plug it in and get the acceleration. That is what I'm being asked to do in part B. Now, if I look at my A equation, tension is negative. I don't like dealing with negatives as much as possible, so it's going to be easier for me personally to rearrange my forces in the x direction for B. So I'm going to have MBA minus, so plus MBG. Now I'm going to take this and plug it into here. So I'm going to have MA G sine theta minus MBA plus MBG equals MAA. So I have gone through, I've eliminated tension. It's no longer an unknown that I need to deal with in this question. So now when I go through and solve, I only have acceleration popping up on both sides of the equation. I can rearrange this and solve. So let's go ahead and do that. So I'm going to have MAG sine theta minus MBG is going to be equal to MAA plus MBA. I can simplify this down to solve for the acceleration. I'm going to have mass of A times sine theta minus mass B, that quantity is multiplied by the acceleration due to gravity, divided by mass A plus mass B. I was given mass A, I was given mass B, I'm given my theta value, I know what G is, I can go through and solve. So I'm going to have 9.8 meters per second squared. My value for A is 21.3 kilograms. Sine, my angle here is 18.4 degrees. Minus mass of B. Again, there's a typo on this version of the slide, so forgive me for that. It should be correct in the blank version that you have. Minus 1.22 kilograms divided by the two masses added together. So we need to take this and plug it into a calculator. So when I took this and plugged it in, my acceleration that I got was 3.569. I have 4.5 here, meters per second squared. The reason I carried so many sig figs here is I do need the answer in part C, so I carried a couple extra ones. It is a 3 sig fig question, so that means that my answer will need to be 3. I like to carry 3 extra ones when I'm doing problems, so that's why I have the 3 here. So my answer for B is going to be 3.57 meters per second squared. This is the acceleration in which box A goes down the incline and box B moves directly up the incline. In This question so far, we have been utilizing Newton's first and second laws. We used the first law in both y directions, in which our force value was 0. We didn't need to worry about it. Then it ended up not mattering in this question. We only needed to focus on the x direction, which had two unknowns, tension and acceleration. So because of that, and we were solving for acceleration in this case, we eliminated tension by rearranging one of the equations, in this case box B, plugged it in to box A, solved for a numerical value. Now what we need to do is go through and solve for C. So we have an acceleration. Again, we just solved for it. We are told that box B is going to be moving a total of 1.5 meters. Sorry for all the dinging from emails. I thought I closed that, but I guess not. So we're going to be moving 1.5 meters, and we are starting from rest. So this is a kinematics portion of a question. Whether or not I do this to you for the final, you'll find out. I'll find out when I write it, but it is something that could pop up. Also could not pop up. Both are equally valid, but there is going to be a kinematics review video. That should be the next one that comes out because that's the one I have written. Ideally, it's coming out same day as this one, but just later. So for this equation, we'll see it pop up in a sec. But so the equation we're going to need to use in this case is going to be final velocity in the x direction squared is equal to the initial velocity in the x direction squared plus 2a, in this case, delta x. Again, we know we're starting from rest, so that's going to be 0. So to solve for the final velocity, I'm just going to take the square root of 2a delta x. I have all these numbers. I can just plug them into a calculator and go ahead and solve. Just double checking my work that I did earlier. So when I did this, I got 3.236 meters per second, or the final velocity of box B right before it's going to hit the pulley and kind of stop the whole question as we have been solving for it. It is going to be moving at 3.27 meters per second. So it is possible for the exam that I add friction, but that is going to be as complicated as the question gets. You're not going to have 2 inclines. You're not going to have 3 objects with 2 different coefficients of friction or anything like that. I'm going to give you a 2 object system with or without friction and with or without combining it with kinematics. That is the type of question you can expect for forces. All right, if you have any questions, let me know.